can do it. There we go. Okay, so 1.5 for today, parent functions and transformations of parent functions. All right, so first of all, we need to kind of make a little bit of a list of what our parent functions are and what they look like. So the first one is going to be the constant function. It's f of x equals some value c, some constant, any number c. So what that one looks like is just a horizontal line at c. All right. And then kind of the next level of parent function is a linear function, f of x equals x. So that's just your standard non-transformed line that goes through the origin with a slope of 1. So that's your basic line function. Then we've got, yes, I did push record. Thanks, Aaron. Then we've got f of x equals x squared, the quadratic. So that's our basic quadratic with the vertex at the origin, opening up. Then we've got the cubic, and that's probably where we will stop with increasing degree of x. So there's your standard cubic function. So those are all of our polynomials. Or I guess these are our, anyway. Then we're going to do the square root, the radical function. Square root of x. Drawing straight lines is hard, apparently. There we go. There's our square root. And then we've got our reciprocal function. And we've seen a little bit of this last week and stuff like that. F of x equals 1 over x. So that's where we've got the asymptote. That is the y-axis and the x-axis. And then we have two more here. We have the absolute value function. That starts out looking like our linear function, but then instead of turning negative, it becomes positive. And then the last one that we have that we'll look at is our step function, or our greatest integer function. And so the notation for that looks like this. If you're just seeing it like in a textbook or something like that, that's typically what it will look like. So that's our function that looks like we've got a dot and then an open dot, and then we jump up a step and jump up a step and jump up a step. Oops, open dot. All right, so there's our greatest integer function. If you're typing into Desmos or something like that, this function, you would do floor of x. All right, so that's what that one also could show up as. So those are our kind of 8 parent functions we're going to be working with right now. And so what we want to be able to do is know what happens when you change those functions a little bit. How do we move them around? How do we stretch and compress and things like that? So this, again, is hopefully something that was covered back in Advanced Algebra Trig, but we're going to go over it again together in pre-calc. Any questions at the moment before we get into changing the function? Okay. So I'm going to show the function transformations in a couple of different ways. The first way is going to be with an example, and then the second way is going to be like the generic function notation way to write it. Okay, so transformations. All right, so we're going to start for our example function. We're going to use f of x equals x squared, because that's a good generic one that it's still easy to see the effect of all of these different transformations and things like that. Okay. Just a minute here. Forgot to do the attendance thing. Okay. All right, so the first one that we're going to have is moving it left to right. Okay, so whenever it's moving left to right or something horizontally is happening, it's going to be grouped inside with the x. So for example, to move something, and it's going to be kind of the opposite of what you would think it would be. So if we're going to move something to the left, this function move to the left would be, I'm just going to call it as x plus 2 squared would be moving it to the left 2. Moving it to the right would be x minus 2. But it would be grouped inside the parentheses with the square on the outside. So that's moving left and right. If I was going to do it with function notation, like if I had my function originally f of x and I wanted to move it to the right, or I mean to the left, that's what it would look like. So if I was just going to describe it based off of what's going inside with my x and stuff like that here, this is how we would do it. Or if I was going to move it to the right, and you'll see this in your IXL section, it'd be the same as doing that. All right, and then moving it up and down is outside. So outside of the parentheses means it's with the y. So if I want to move or translate it up and down, if I wanted to move this one up 2, it'd be x squared and then plus 2 on the outside. So moving things up and down goes the way that you would think it would be. Moving it up is a plus, moving it down is a minus. Or if I was using just function notation, f of x, if I was going to move it up, I'd stick a plus 2 on the outside. Or a minus 2 on the outside to move it down. Okay. So moving things up, down, left, and right, those are kind of the basic examples and things like that that people tend to not have as much trouble with. It's the compressing and stretching that tend to give people a little bit more trouble here, because they're related to one another. So we're going to start off with vertical. Stretch and compress. All right, so if I want to stretch something vertically, I would just stick a positive number out front. So in this case, if I wanted to stretch it by a factor of 2, I'd have 2x squared. Or if I was using function notation, f of x would go to 2 times f of x. That would stretch it vertically by a factor of 2. And we could also compress it vertically. So compression is going to be where you stick a fraction out front that has a value between 0 and 1. So I could stick it 1/2 out in front, and that would compress it by a factor of 2. And if I was showing it with function notation, it would go the same way. For horizontal, it's kind of the opposite of what you would think, just like it was up here, and it has to be in the parentheses with the x. So horizontal, stretch, and compress. So if I was going to horizontally stretch this, maybe I would put a 2 inside with the x and then square it. But the factor that it's stretching it by is then, or sorry, that's not stretch. Horizontal stretch is, sorry, it's the opposite. It's 1/2. So yeah, horizontal stretch goes kind of with vertical compression. They are related to one another. So these two are similar, and then these two are similar. And so then this is horizontally stretched, but it's by a factor of, if you were to multiply, or not multiply, if you were to take this to the second power, that's the factor that it's stretched by, because it's inside with the x. So whatever you do with the square, you have to distribute, since it's in the parentheses. You have to give it to both of them. And so then compression would be a similar idea here. You'd have, but it'd be a positive or negative, but it would have a something with a greater than 1 be your coefficient. So in this case, this would be horizontal compression. And it'd be by a factor of 4, because you would give the square to both of them. So if I was going to do it with function notation, horizontal stretch would look like that. Horizontal compression would look like that. Okay. And then the last thing that we have is reflecting over the axes. So reflect over, we could do it over the y-axis. Spelling is hard. A-X-I-S. And then over the x-axis. So if I took x squared and I wanted to reflect it over the y-axis, reflecting over y means putting it inside with the x. Which makes sense if you think about what a quadratic function looks like, right? If I were to reflect a quadratic over the y-axis, it shouldn't really change its shape, right? It's going, or it shouldn't change what it looks like too much, because because when you look at the way that you would do that, you've got negative x and it's squared. That's just the same thing as regular x squared, since squared things are positive. So, but if I were to flip it over the x-axis, then it would look like that. Which is why when we are flipping something over the x-axis, the negative goes up on the outside of the parentheses. So reflect over the y-axis, the negative goes inside with the x. Reflect over the x-axis, the negative goes outside. Okay. So that's kind of the basics of how those things all work. Let's see. Let's do some examples where we're gonna do a couple different things. We're gonna look at graphs that have been moved around or compressed or stretched and things like that, and figure out what happened to it from the graph. And then we're also going to look at equations, at functions that have been transformed, and tell from just the function itself what has happened to it. So let's start with, let's start it down here. An example. We're going to say f of x, the parent function, is the absolute value of x. G of x, the new function that's been transformed, is going to be 0.5 times the absolute value of x plus 4. Okay. So if you're just asked to graph them and then determine what happened, there's a couple different ways you can go about it. You can try to determine what happened before you graph it, or you can graph it and try to kind of determine what happened simultaneously. Before we graph it, let's go ahead and take a look at what we think might have happened here. Okay, so first, these are the two things that are different about this one. What is that 0.5 telling me? Is it, first of all, are we dealing with vertical or horizontal? What do we think? Are we doing something vertically to it or horizontally to it? Yep, vertical. Because it is outside those absolute value signs, just like these are outside the parentheses. Then are we stretching it or compressing it? If it's 0.5, are we stretching or compressing? Yes, 0.5 out in front means we are vertically compressing this thing. So we know we've got vertical compression. So it's going to look shorter and fatter. And then we've got, it's either moving left, right, up, or down. What direction are we moving this thing? Yeah, we're moving it to the left, everything you own in a box to the left. Moving it left 4. Okay. So then we might be asked to graph the parent function and our transformed function. And we should be able to do that just from what we're given here, but we can also use something like Desmos to graph it if we want to. So we'll show both. How we would graph it without a Desmos and how we would graph it with a Desmos. So the original absolute value function, f of x, would just look like that, right? And I just went out 5 in all directions. So then if we're moving it to the left 4, this vertex is going to be over 1, 2, 3, 4. So that's what I would probably start with if I was going to graph this by hand. And then since this is vertically compressed and the factor is 0.5, that means it's going to have a slope now of 1/2. So I go up 1/2, 1/2, and it ends up looking something like that, and going out by that same slope in the other direction. So the pink one is g of x, the green one is f of x, and that would be our new graph. Well, let's take a look at what it would look like on Desmos. I'll give everyone a chance to finish writing here real quick. if you haven't yet. And then we're going to jump over to Desmos. You can also do this on a TI calculator just using the graphing function. So we had absolute value of x. That was our f of x. And then g of x was 0.5 absolute value of x plus 4. And there it is. So we have it moved over to the left 4, and we have it crossing the y-axis at 0, 2, just like we had on the hand-drawn one that we did. Okay. Any questions so far? Any things we're not sure how we got them? Numbers that don't quite make sense? Okay. If at any point you do, feel free to type in the chat or unmute yourself and say so. Because if you have a question, I'm sure someone else in the room has, or in the Google Meet has the same question. Okay. So that's pretty much what we're going to be expected to be able to do here. Go from a parent function to another function and describe what happened to it, and then graph it. And you can always graph using a graphing calculator, or you can graph it by hand, either way. But let's try another. Let's go. This time, f of x is going to be x squared. G of x is going to be 2x squared minus 4. Okay, so in the chat, tell me what happened to it. Did it get stretched or shrunk or compressed? Did it move left, right, up, down? What happened to it? What do we think? All right, I'm seeing a common theme of down 4. That's good. And a common theme of vertical stretch. Yes. All right. So these are the things that are telling us what's happening. The 2 out in front, if we look back at our other set of notes, the 2 out front is telling us that it's vertically stretched, and it's exactly the example that we used there, actually. And then down 4, since the 4 is outside. Okay. So we can graph this with a Desmos. We can graph this without a Desmos. Either way. Regular x squared would look something like that. We'll go ahead and use a Desmos to graph these if we want. Let's go, so make it a little bit quicker. X squared, and then we had 2x squared minus 4. Okay. So the vertex should be moved down 4, and then we should also notice that it looks skinnier, right? So it should look taller and skinnier. If it's been vertically stretched, it does look taller and skinnier. And then we've got the places where it crosses with your original. So those could be good things to denote in your graph. So let's see, we go down 1, 2, 3, 4. I didn't draw my original very well, but there we go. So yeah, whenever you're hand drawing graphs, especially if you don't use graph paper, things can get a little bit dicey. So mine doesn't look perfect, but that's about what it should look like. If you want to call out some points, you can, that this is 2, 4, and -2, 4. And that one's a pretty obvious one that you can usually see. But that's the idea here of what we want to be able to do. Okay. The other thing that we want to be able to do is tell what happened just using function notation. So we'll do a couple of function notation examples here real quick. So if I say f of x is being transformed, and it's happening, like we'll go x. We want to be able to read those instructions to tell us what is happening to the function. So what do we think is happening to this function? We've got two things going on. -4 and +7. What's the -4 and the +7 telling me? Go ahead and type in the chat. Yeah, we've got this. Right 4 and up 7. Yeah, so this is the kind of function notation way of doing things that we saw up here, where these inside with the x, we're moving it left and right. Outside with the y, we're moving it up and down. So right 4 and up 7 is what's going on here. Awesome. Let's do another one. All right. This time we're sticking a negative in there. So with this one, we've got something happening here and something happening here. What do we think's going on? First of all, which axis are we reflecting over, x or y? What do we think? The negative's on the outside. Yes. All right. 3 of us got it. It's flipping over the x-axis. The negative on the outside tells me it's reflecting over the x-axis. So first thing I would say is reflected over x-axis. All right, then we've got this 2 in here. What's that 2 telling us? If it's inside with the x, are we dealing with horizontal stretching, horizontal compressing, vertical stretching, or vertical compressing? All right, got the horizontal part right. Yeah, the horizontal one, it's always kind of hard to tell if it's stretching or compressing horizontally. In this case, it is compressing. It's kind of the opposite of the way that the vertical one works. So if it's a number greater with the absolute value greater than 1, for x, for inside, for horizontal, it's going to be compressing. So this is horizontal compression. All right. So that's the other kind of thing that we want to be able to do. Any questions at the moment? Any numbers we're not sure where they came from? Steps we're not sure why they happened? Anything like that? This is pretty much everything new that we're learning for the day. So especially this function notation stuff, that might be new. I don't think we did that particular way of phrasing things that much in Advanced Algebra Trig. But the idea of transforming functions should be somewhat familiar here. But we're going to get more practice with it. Okay, so this is the part where we get the assignment, where we can ask questions about the assignment and all that good stuff. So here we go. Classwork. For our assignment today, we have two things. We have one IXL section that has function transformation rules practice. So that's going to be like the examples that we just did, where we see things like this, and we're asked, what is happening? Is it going up, down, left, right? What's going on? So we would say, oh, since it's +1 inside with the x, that's moving it 1 to the left. With this one, since the -7 is on the outside, we say, oh, it's moving it down. Things like that. All right, and then the worksheet is going to be a little bit more like the first couple of examples that we did, where you graph some things and then describe what happened to go from f of x to g of x. Whenever it says to describe how the graphs are related, that means that you want to basically talk about the transformation, what happened to go from one to the other. So we've got 6 of those problems. All right. So we will have an exit ticket towards the end of class, and I will be here the entire period. But unless you have questions or comments or concerns, you are free to head on out and enjoy your Friday.